Hello everyone, thank you for joining me. Today we're going to talk about Math 121 section 1.2 and we'll get started with a couple definitions. First, parameter and statistic. These are dual definitions in that they will be related in some way or another, and that'll be a theme throughout this chapter. A parameter describes a population. A parameter is anything that's describing the population. Maybe it's, a mean, an average about the population. That would be a parameter if it describes the population. Whereas a statistic describes a sample. So parameters describe populations. Statistics describes samples. Alliteration helps us. Parameter, population, statistics, sample, PPSS, PPSS, alliteration, right? Parameters describe populations, statistics describe samples. So, example, there are 17,246,372 high school students in the U.S. In a recent study of 8,505 of these students, 44.5% said they had texted while driving at least once in the previous 30 days. Which of these values are parameters and which are statistics? So let's write parameters and statistics. 17,246,372, that's a parameter. That's the population in question. So 17246,372 is our first parameter. So that was the first number. That was a parameter. Described the population. High school students. And then the next number, in a recent study of 8,505 of these students, that's the size of the sample. So 8,505 of the students. That's a statistic, right? It describes the sample. The next number is 44.5%. Is that a statistic or a parameter? Well, it's talking about this group has this quality, so it's a statistic again. 44.5% is a statistic. And then the next number is 30 days. Is that a parameter or a statistic? Neither. It's not describing either the sample or the population, right? It's just part of the study. That was the time frame they wanted to look at. That is neither a parameter or a statistic. That is just an arbitrary number signifying the time frame of the study, right? So, parameters and statistics. Our next dual definition is quantitative data, also called numeric data, and qualitative data, also called categorical or attributive data. So these two types of data are another dual definition. Quantitative data consists of numbers or counts, numbers representing, I skipped the word representing, counts or measurements. They're numeric. They are numeric in nature. They represent numbers. They're counts. You're counting things. You're measuring things. Quantitative data. Whereas qualitative data, which can be called categorical or attributive, consists of names or labels. Qualitative data consists of names or labels. Now, we have a warning here. Numbers can be qualitative, and we'll have an example of that on the next page. It is important to always include and consider the units when working with quantitative data as well. It's always important to know what the units are, because depending on the units, that might determine whether you can run certain statistical analyses or not. So always good to know your units. That's just generally true in mathematics. Always have units. Always, always, always put your units on things. So let's have some examples of quantitative data and qualitative data. An example of quantitative data might be age. That would be an example of quantitative data. Or maybe height. Or maybe weight. Right? They're measurements or counts. Age is a count, right? It's how many years you have been alive. Height is a measurement. How tall are you? Weight is a measurement. How much do you weigh? Now, qualitative data. Maybe an example of this would be gender, or eye color, or college major. Or zip code, or social security number, your SSN. Well, then the last two were numbers. How can numbers be qualitative and not quantitative? Well, zip codes. Are zip codes numeric? Do they represent a count or a measurement? No. They're labels, aren't they? For example, Saranac Lake has a zip code, right? That's just a arbitrary replacement for the name Saranac Lake. It's a label. Even though it's a number, it works as a label. Same with your social security number. Is that a measurement? No. It's not a count either, right? When you were born, you were given a social security number. It's a label. It's a way to identify yourself with a label. That label happens to look like a number, right? But it does not behave like a number. You can't add zip codes together. You can't multiply social security numbers. They're not numbers, right? Even though they look like numbers, they aren't really numbers. They're not numerical. So that's the difference between qualitative, think qualities, and quantitative, think quantities, right? So next, we have another dual definition. First, both these definitions are more rigorous classifications of quantitative data. So this is numeric data being broken down a little bit further. So let's take a look at discrete data first. This is when data is finite or countable in nature. It's either finite many options or countably many options. Whereas continuous data has when data has infinite and uncountably many possibilities. You can't count out all the possibilities for continuous data like you can with discrete data. Now these can be easy to jumble in your head, and the book gives a helpful little way to remember it. First, note these two definitions can be difficult to understand. I recommend spending extra time contemplating these meanings and ensuring you understand the differences. The following comes from the book. The concept of countable data plays a key role in the preceding definition, right? Countable. But it is not particularly easy to understand. Continuous data can be measured but not counted. If you select a particular data value from a continuous data set, there is no next value. There's no next value in the data set. This might be easier to see once we have our next examples. So keep this in mind as we look at the next example. Discrete versus continuous. What's an example of discrete data? Well, maybe number of pets. Maybe coins in pockets. How many coins are in your pockets? That could be countable or discrete. Number of flips on a coin before a heads is flipped. The number of flips on a coin before a heads is flipped. That could also be countable data, right? Could that be infinite? Could you theoretically sit down and flip a coin an infinite number of times and never flip a heads? Not very likely, but it could happen. You're never guaranteed to flip heads on a coin, right? It could be infinite, but you can still count them, right? One flip, 2 flips, 3 flips, 4 flips, and so on and so forth. Last example might be number of subjects in a experiment. Maybe we've got some number of subjects in experiment, right? Whereas continuous data, how would continuous data look? Well, maybe we look at temperature on a thermometer. How many possibilities are there on a thermometer? You know, those little mercury tubes you put in your mouth? How many possibilities could you have? An infinite number, right? You could have any number on that thermometer and any value in between. Think about it like if these 2 markers are the 2 dash marks on a thermometer. You could be anywhere in between them, right? You're not guaranteed to fall on a whole valued number, right? Decimals are fair game. That's one possibility. Another possibility in a continuous scale would be weight. When you weigh yourself, what's the limit for how specific you can weigh yourself? Well, that's how accurate your scale is. If you have a scale that is, you know, extremely accurate, like a triple beam balance from science or something like that, you can have a continuous amount of weights. There's not just one value you can have. Somebody could weigh 180 pounds. What's the next weight after 180 pounds? Is it 181 pounds? No, someone could weigh 180.5, right? So a good way to think about this is decimals are commonly found in continuous data. If you have decimals, then your data is most likely continuous. Not always. Let's think of a decimal example for discrete data. Money. Money is decimals, right? But if I give you a money amount, $5.73, what's the next money amount? $5.74. If I say 1,000 bucks, the next money amount is $1,000.01, right? A penny is the smallest unit. It's discrete. Even though it's decimals, it's discrete because there's a limit to the number of decimal spaces you can have. Whereas with your weight, could somebody weigh 180.47892 pounds? Yeah, there's no reason somebody can't weigh any weight. You can weigh any number. All the decimals are fair game. You just need to get a scale that's accurate enough to go to how many decimal places you want, and then you can see the full continuum, the full spectrum of data. So continuous data, I like to think of decimals with continuous data. Whereas discrete data, I like to think of, can I count out all the options? Can I list all of the options? Could I write them all out? If you gave me an option, could I find the next option? If somebody said they have 5 pets, what's the next choice for the number of pets? 6. If someone said they had 83 coins in their pocket, what's the next choice for coins in pocket? 84. You can count. You can find the next value. If someone says they wear a size 9.5 shoe, what's the next shoe size? A 10. If someone says their foot is 10.6 inches long, what's the next possible length for a foot? Could be anything, right? It could be 10.65213, could be 10.7, maybe it's 11. Length of foot in inches and shoe size are 2 ways to measure the same thing. One is discrete, shoe size. You can list all of the shoe sizes out. The other one, foot length in inches. continuous. You cannot list all the possible foot lengths someone could have. So you can measure the same thing in both fashions. You can measure, shoe size and foot length in inches are both measuring the size of people's feet, but in two different ways, right? So that's discrete versus continuous. Countable versus infinitely uncountable. Next, we move into our last batch of definitions that are paired together, and these definitions deal with the level of measurement. Now, I put this table here. I generally like to think of the table from top to bottom, rather than bottom to top. And this table shows the 4 levels, provides a brief description, and a couple examples. The primary goal in identifying the level of measurement is determining which statistical methods are appropriate. As we advance in the semester and as you advance in statistics, you'll learn that not all statistical tests can be applied to all data. You can't always apply statistical tests. Certain tests require nominal, ordinal, interval, or ratio data in order to be run. So it's important to know what tests you can use on the data you have. And if you don't know what level of measurement your data is, you can't know what tests to run. So let's look at the types. Let's start with nominal. I said I like to start at the bottom and work my way up. Nominal data is categories only. The data cannot be arranged in order. So it's data that is categorical and has no order. An example would be eye color. Eye color, they're categories, right? Blue, brown, black, green, hazel. They're categories. Is there an order? Which eye color comes first? Which one comes second? There's no order, right? Now somebody might be saying, oh, what about alphabetical? What language are you alphabetizing the eye colors in? Is blue always going to come after black? No. Depending on what language you are, those colors might be in different orders, right? So there's no order with eye color. The next category up is ordinal data. Here, data can be arranged in order, but differences either can't be found or are meaningless. There's no idea of subtraction. You can't subtract the values in ordinal data. They have an order, but you can't think about differences. An example would be ranks of colleges. If a college scores 3rd best in the country and another college scores 6th best in a country, those have an order, right? 1st, 2nd, 3rd, 4th, 5th, 6th. But can you subtract 3rd place from 6th place? What does that mean to subtract those numbers? There's no meaning behind differences. There's no meaning behind the subtraction in ordinal data. Next, interval data. Here, differences are meaningful. You can subtract things and it does mean something. But there is no natural 0. The value of 0 does not mean 0. And ratios are meaningless. Ratios are fractions. You can't compare the numbers as fractions. An example would be body temperature in degrees Fahrenheit or Celsius. Now, there's a 0 degrees Fahrenheit, right? Does 0 degrees Fahrenheit mean there's no temperature? No, 0 degrees is still a temperature, right? We just chose to call that temperature the number 0. That's not a true 0. Also, let's think about ratios. If I tell you it's 35 degrees outside, does it mean it's twice as warm when it's 70? No, the concept of twice doesn't make sense with temperatures, right? Is 20 degrees twice as warm as 10 degrees? No. Multiplying temperatures does not make sense. Thinking about ratios, the idea of twice, trying to set up a ratio does not make sense. And the 0 is not a real 0. 0 degrees Fahrenheit is still very much a real temperature, right? Whereas with ratio, there is a natural 0, and ratios do make sense. An example, height. What does it mean to be 0 inches tall? Do you have a height if you're 0 inches tall? No, that's nothingness, right? 0 is nothing when measuring height, or length, or distance, or volume. If I tell you something has 0 volume, does it take up space? No, it has no volume. The 0 is meaningful. Can you be twice as tall as somebody? Yeah, if you have a younger brother or younger sister who happens to be quite a bit younger than you, and they're, 3 foot even, and you're 6 foot even, you're twice as tall as them, right? 2 of them makes 1 of you. There are ratios. The 0 is meaningful, and the ratios make sense. And that is the breakdown of the different levels of measurement. Now, let's take a look at some identification examples. Let's identify which levels of measurement each one of these are. So these are multiple choice. Our choices are nominal, ordinal, interval, and ratio. Let's walk through. Course letter grades of A, B, C, D, and F. So right away, I notice there's an order. I immediately can eliminate nominal data. It's not nominal. Nominal says no order. So I know it's not nominal. Next, I check if it's ordinal or interval, right? I go up the list. Is it ordinal? Can I subtract letter grades? What's B minus D? Oh, that doesn't make sense. So it must be ordinal, right? There's no concept of differences, so it's ordinal. How about birth years of famous historical figures? Well, let's see. They have an order, right? Can you subtract years? If I take 1995 and subtract 1990, that has a meaning, doesn't it? That means 5 years had passed. 5 years of time is the difference between there. The subtraction means something. So there are differences. So I've eliminated nominal because there was an order between years. I eliminated ordinal because I can subtract years. Now I'm between interval and ratio. This winds up being an interval because the year 0 is still a point in time, right? It doesn't mean there was no time. The year 0 is still a point in time. It was sometime during the Roman Empire. That was a moment in history, right? So this is interval because the 0 is not true. Lengths of statistics classes at different colleges. Lengths. Lengths are going to be numeric, right? Minutes, seconds, hours. They have an order. Longer time versus shorter time. You can subtract times. 20 minutes and 30 minutes have a difference of 10 minutes. And 0 in terms of time truly does mean 0, right? 0 seconds is no time. 0 means 0. This one is ratio because there was a true 0. Next, daily volcano temperatures in degrees Celsius. Well, I already know their numbers, and I already know temperatures have an order, and I know temperatures do not have a true 0. That automatically means it has to be interval. Temperatures are always interval, right? Because you can always subtract and compare temperatures, but you cannot have a true 0. 0 degrees Celsius is still a temperature. Next, survey responses of yes, no, and undecided. Well, right away, I already see it has to be either nominal or ordinal, right? You can't subtract these. There's no way I'm able to subtract the words yes and no. So the question now is, are these ordered? Do they have an order? And no, they are not ordered. Which comes first, yes or no? Which comes second? There's not a natural order among them. The letter grades had a natural order, right? A, B always follows A, then C, then D, then F. Those are the letter grades. They have a natural hierarchy. Yes, no, and undecided do not have an order. If you think yes should always come first, it depends on the question you're asking, right? You might think no should come first to certain questions. So this is nominal data. Then next we have heights of windowsills in Saranac Lake homes. So heights. I'm immediately thinking about heights. It doesn't matter what heights I'm measuring, right? The measurements are arbitrary. The important thing is that I'm measuring a height. Can I subtract heights? Is there differences? Yeah, there's differences, right? So I know it's interval or ratio. I got to think about the 0, though. What does 0 mean for height? That's a true 0, right? If something is 0 inches tall, it has no height. That is ratio. And then lastly, finishing positions of marathon runners in the Olympics. First, second, third, fourth, fifth, etc. Well, they have an order, right? I just listed them in order. They naturally have an order. Can I subtract? If I take second place and minus fifth place, what does that mean? It doesn't mean anything, right? You can't subtract race positions. It doesn't have a meaning, because are each finisher positioned evenly apart? No, maybe second and third place were super close, but then fourth place was way behind them over here, right? You can't compare them with subtraction. So that would make it ordinal because it had an order. Now notice how with each of those, I talked my way through them. I reasoned them. I walked through the definitions and made sure I was in the right ballpark before I put my answers down. You should be doing the same when you're working with the definitions. Make sure you're thinking about them clearly and walking through the steps of the definition to make sure you are classifying the data correctly. I'm going to be honest with you, these 4 definitions can be extremely easy to jumble in your head. They're difficult to get used to. So practice, practice, practice. I recommend flashcards or, making notes, whatever helps you remember them. For me, flashcards always helped with definitions, so feel free to make flashcards for these definitions. Like I said, they're easy to confuse them. The last thing for today's section will be this note from the book talking about ratio versus interval. It gives a little bit of a hint. I'm not going to read it out loud. You all can read just fine. It'll elaborate on some of the things I said. But remember, we were talking about ratios and true zeros. Those are the keys when you're talking about ratio versus interval. I always like to focus on the zero, but some people like to focus on the ratios. Our author focuses on ratios rather than zeros. To each his own, right? Both will work. So that will be it for today's section. Thank you all for joining me, and I will see you next time.